Okay, hello everyone. So we recently concluded chapter 4, which we discussed about how to solve second order linear, homogeneous and non-homogeneous differential equations, right? Now, what are the applications of these second order differential equations? We spent quite a time on chapter 4, right? It turns out the applications are amazing and the applications are very broad in engineering and other fields. Hopefully, you get to see how powerful differential equations are in this chapter. Okay, really the application that we are focusing on is a spring mass system. So you have a spring, you attach a mass to it, and we are going to analyze the motion that happens after that. Now you would think, well, hang on a second, how it is connected to engineering? Let me give you a couple of good examples. Okay, let's say you have an aircraft or an airplane. Now when the plane is in the air, you have wings on this plane. Think if the wings start to oscillate because of the wind. Of course it's going to oscillate, right? But a little bit. But when you're modeling this plane, you should be very careful that your wing is not vulnerable to larger oscillations, right? That's a differential equation there. We're going to discuss that. And the other example is a bridge. So if you're a civil engineer, so you're making this bridge, okay, modeling this bridge, and if your bridge is vulnerable to storms and winds, and if it is starting to oscillate like vertically, that will be horrible, right? So these things are modeled by differential equations. How to, for example, make a good bridge that is not vulnerable to these oscillations. So this is where we start. We are not going to go into that broad sense, okay? But this is a start. You will learn these things when you're taking engineering courses, hopefully, okay? All right. So let me set few things straight here, beginning of the lesson. The independent variable in this application is going to be time, t. Usually we use x as the independent variable, but here in this lesson we are going to use x as the dependent variable. Now this is very crucial, don't get mixed up. The dependent variable, we usually write it in the top, right? The independent variable in the bottom. And the other thing is this x, of course, t is time, x is the displacement. So when you attach a mass, it's going to get a motion. So it's x represent the displacement from the initial position or the rest position. Okay, all right. And we are going to discuss about homogeneous and non-homogeneous differential equations. But really the non-homogeneity means application-wise, a physical sense, is the driving function or the forcing term. Okay, we'll see that when we move on. So what is the scenario that we are discussing about? Here are the three stages. So initially you have a spring. Okay, let's say the length of the spring is L, simple L. Now what you're going to do is you're going to take a mass and you're going to attach it. Instantly, what happens is it's going to stretch little bit, right? Okay, so let's say that stretch is a simple S. Now the total length of the spring is going to be L plus S. Now it's still, you don't have a motion. This is an instantaneous result, right? A stretch. So we call this the rest position, the instant that you attach the mass to the spring. Okay, now when you let the mass go, or if you put an external force, so sometimes it happens naturally, then the mass or the spring is going to stretch, or the mass going to start moving from the rest position. So the simple x is actually the displacement from this rest position. That's crucial to understand. Okay, and if the motion is downwards, x is positive, and if the motion is upward, we say x is negative. Okay, so those are a few things that we need to set straight in the beginning of the lecture. Okay, the other thing is, well, the mass of the spring is of course negligible. Okay, so we have that assumption all the way. Now, what is the equilibrium position here in the system? In the physical sense, the equilibrium position is actually the instant that you attach the mass, or the L plus S is the equilibrium length, right, or the rest position. Now let's take the general scenario. When you attach this mass, right, you get this L plus S instantaneously. But when you let the motion happens, it's going to not go forever, right? There will be frictions or other type of forces, and the motion is going to stop, right? So what is the position that motion going to stop? What will be the ending displacement? The ending displacement is going to be 0, right? X is going to be 0. That's the end of the motion. Now, what is the rest position? It's L plus S, right? Not L, it's L plus S, okay? All right, so let's try to come up with the model. Now, the model is based on two laws. One is Hooke's law. So the Hooke's law is actually you exert this force on the spring, and this force is actually proportional to the distance the spring get stretched or compressed. So for example, the force that exerted on the spring, let's say in the opposite direction of the motion or the vertical displacement, so let's have a negative, is actually proportional to the stretch. So a constant times a stretch. So the proportionality goes away. If you want the equal sign, you have to have a constant. So this K is like the Hooke's law's constant, okay? And S is the amount that it stretched. Now this is actually in the instantaneously, right? And then when it's on the run of the motion, it's actually negative K X plus S, right? The displacement plus the stretch. Overall, that is the total stretch, right? The displacement plus that instantaneous stretch. So this is Hooke's law. Let's remember that. And then the other thing is damping. Damping is a very crucial fact here. Now, what is damping? Again, when you let the mass run in the motion, you're going to get amplitude, or you're going to get oscillations, right? That is the precise explanation. Now, when you get these oscillations, because of the energy drain. Now, why energy drain happens? You might have friction on the system, or the motion is going to stop, right? Because the energy is going to drain from the system. So you would see what happens in this mass is it's going to have larger oscillations, and it's going to get smaller and smaller, like the speeds runs out, and at the end, eventually, the motion stops because of the energy drain. And the oscillations will be like, so you can see the amplitude gets small, right? So that amplitude discrete is called the damping, okay? So damping is, for damping forces, F sub D is proportional to the speed, and beta is the damping constant, okay? So damping forces and the Hooke's law, negative K X plus S. So the other thing that we use is, of course, Newton's second law of motion. We have motion, and whenever you have motion, Newton's second law appears, right? So Newton's second law says sum of all these forces are equal to mass times acceleration. So some of the forces are, well, the Hooke's law and the damping forces. You can get external forces like wind or magnet something, and then the gravity or the weight of the mass, right? So all these forces are added equal to mass times acceleration. Now we know, let's say that external forces are simple F, okay? It's a function of time. We'll get to, later we'll learn why. And F sub G, that's the gravity, that's the weight. Now here one important thing is, whenever a question is given, you have to read very carefully and understand whether the weight is given or the mass is given. Okay, so that's two different things. You have to read carefully, just a heads up, okay? G is the gravity, of course. So when you have these all forces, we have this differential, we have this equation, not differential yet, well, sort of, yes. Now acceleration is rate of change of speed. Now what is rate of change of speed? Rate of change of speed is the second derivative of the displacement, right? Because v is the rate of change of displacement. So this is actually the second derivative. So we can write dv over dt as second derivative of x with respect to time. So then m times a is actually now second derivative of x with respect to time equal to damping forces, Hooke's law, external forces, and mg weight. Okay, all right. So if you now simplify, now speed, here we have speed on the damping forces. Now speed is actually dx over dt, so we can write it there. And if we expand k, you get negative kx and negative ks. Now when the mass is on the rest, actually the weight is same as the Hooke's forces, the forces from the Hooke's law. So mg minus ks turn out to be 0, right? Mg is equal to ks means mg minus ks is 0. So this right hand side will simplify it to actually m times, so that's this is the left hand side, actually minus beta dx over dt, now minus kx, ks and mg gone, plus ft, f function of time. Okay, so let's take these terms onto the left hand side and let the function f, or the external forces, to be alone on the right hand side. So what we get is really this differential equation here. Now that is the model that we need. Now usually in chapter 4, remember, we use the standard form. That means the coefficient of second derivative is 1. But here it's m. So let's divide by mass. Okay. So when you divide by mass, what you're gonna get is actually t squared, d, second derivative of displacement, plus beta over m, that is mass, plus k over m, x is equal to the f over m, right? Okay, so now let's say, let's define, okay, this beta over m to be 2 lambda. So why 2 lambda? Lambda is just arbitrary letter that I choose. Why 2? Let's see it later, because it helps our simplification when we are solving them. Okay, so just for now, that's I arbitrarily choose 2 lambda. Okay, and let's say k over m to be w square. Now why w square? That's to help us simplification in later in the chapter. Okay, so f over m, let's call it g. Okay, this is the model for the motion of a spring mass system. Okay, now final note, this second term here, 2 lambda times dx over dt, what does it model? Lambda is actually beta over m, right? Now what is beta? It has something to do with damping, right? Beta is the damping coefficients. So really this 2 lambda times dx over dt is what takes care of damping. Okay, and w square times x is, that is what takes care what happens with the Hooke's law, the stretch. Okay, and g is actually the driving force. Now notice g is only a function of time, because this is a linear differential equation, right? The driving forces, it only depends on time. If the driving force depends on the displacement, this is a non-linear differential equation, right? Because the non-coefficient function should not be a function of dependent variable if you want a linear differential equation. Okay, so now you can see we have a differential equation model, second order. You can see the coefficients are constants, lambda, w square, they are constants, and non-homogeneous differential equations. We are going to use what we learned in chapter 4 to solve this, but we have a lot of application to learn within this model. Okay, we'll get to them in the next couple of videos. Okay, all right, thank you.